For billions of years, the world's most precious stones were forged in the chaotic depths of the Earth's mantle, under crushing pressures and blistering heat. But today, engineering has achieved the impossible, replicating the Earth's most extreme environments inside a controlled laboratory. This is the story of how we turn ordinary carbon into the hardest material known to man. At its core, a diamond is nothing more than carbon atoms arranged in a crystal lattice, a structure so strong and stable that it resists almost any force. To build one, engineers must master the forces of nature, recreating pressures exceeding 725,000 pounds per square inch, or temperatures hotter than the surface of the sun. Whether it's for a high-end engagement ring or a precision industrial cutting tool, the journey from a puff of gas to a sparkling gem is a masterclass in extreme physics and chemical engineering. In this deep dive, we'll explore the two primary methods of creation: the brute force of high-pressure, high-temperature systems, and the sophisticated molecular layering of chemical vapor deposition. Welcome to the future of alchemy. Every masterpiece needs a foundation. And in the world of synthetic diamonds, that foundation is the diamond seed. These are tiny, wafer-thin slices of pre-existing diamond crystals, often no larger than a grain of sand or a fingernail. The seed acts as a chemical blueprint, a template that tells the new carbon atoms exactly where to land and how to bond. If the seed is flawed, the grown diamond will be flawed, which is why these starters are polished to an atomic level of smoothness using specialized abrasive pastes. Once prepared, the seeds are placed inside a growth chamber, their orientation carefully calculated to encourage the building of a specific crystal structure. Think of it like a biological cell, providing the DNA required for a new organism to grow. Without this microscopic guide, the carbon would simply settle into graphite, the soft gray material found in pencils. By providing a diamond seed, we force the laws of thermodynamics to favor the creation of the world's most rigid structure. Each seed is a promise of the brilliance to come, waiting for the furnace to breathe life into its crystal lattice. The first method of creation is the high-pressure, high-temperature process, or HPHT. This machine is an engineering titan designed to mimic the conditions 100 miles below the Earth's surface. At the heart of the press is a small growth cell containing the diamond seed, a source of carbon, usually high-purity graphite, and a metallic catalyst, often a mix of iron, nickel, or cobalt. As the press activates, it exerts a staggering 5 to 6 gigapascals of pressure. To put that in perspective, it's like balancing the entire weight of a commercial jetliner on the tip of your thumb. Simultaneously, electrical currents surge through the cell, heating it to over 1400 degrees Celsius, or 2500 degrees Fahrenheit. Under these brutal conditions, the metal catalyst melts into a liquid pool, dissolving the graphite carbon. Because the system is carefully tuned, the carbon atoms migrate through the molten metal and settle onto the cooler diamond seed. One by one, atom by atom, they lock into place. Over the course of days or weeks, the tiny seed grows into a large, rough diamond crystal, emerging from the cooling metal like a treasure from a sunken ship. While HPHT relies on brute force, the second method, chemical vapor deposition, or CVD, is an exercise in molecular precision. It begins in a vacuum chamber, where air is replaced by a specialized gas mixture, usually hydrogen and methane. Methane provides the carbon, while hydrogen acts as a selective etcher, preventing the formation of non-diamond carbon. To kickstart the process, engineers use microwaves or hot filaments to ionize the gases into a glowing plasma. This plasma is a high-energy soup of charged particles, reaching temperatures that would melt a steel beam instantly. Inside this purple glowing cloud, the methane molecules are ripped apart, releasing individual carbon atoms. These atoms rain down onto the diamond seeds below, which are heated to a precise 800 degrees Celsius. This temperature is critical. It's hot enough for the atoms to move and find their proper place in the lattice, but cool enough to prevent the whole structure from collapsing into graphite. It is a slow, methodical rain of atoms, building the diamond upwards layer by microscopic layer, at a rate of roughly 0.5 to 1 millimeter per day. In the CVD chamber, we aren't just growing a rock, we are literally growing physics. Whether it's HPHT or CVD, the ultimate goal is the same, the perfect crystal lattice. In a diamond, every carbon atom is bonded to 4 neighbors in a tetrahedral arrangement. This is the strongest chemical bond in nature. But even in a lab, achieving perfection is an immense challenge. Engineers must monitor the gas purity to parts per billion. A single stray nitrogen atom can turn a diamond yellow, while boron will tint it blue. While jewelers might find these colors beautiful, for high-end technology, such as quantum computers or high-power lasers, these impurities are defects that must be eliminated. Modern sensors track the growth in real time, adjusting the microwave power or the hydraulic pressure in micro increments. We are managing a delicate dance of energy and matter, ensuring that each new layer of atoms bonds seamlessly to the one below it. If the growth happens too fast, the crystal becomes strained and may shatter when removed from the chamber. If it's too slow, the process becomes economically unviable. It is a balancing act performed at the scale of nanometers, where the margin for error is zero. After weeks of growth, the time comes for the harvest. In HPHT, this involves breaking away the metal flux and ceramic shell, revealing a blocky, often yellowish or clear crystal. In CVD, the result is often a hockey puck or a square plate of dark-edged diamond. At this stage, they don't look like the gems you see in jewelry stores. They look like industrial glass or rough cubes of rock. These are known as rough diamonds. But don't let their appearance fool you. They possess the exact same chemical, physical, and optical properties as their subterranean counterparts. They are just as hard, just as thermally conductive, and just as capable of refracting light. Before moving forward, each rough stone must be cleaned in a series of boiling acid baths, usually a mixture of sulfuric and nitric acid. This removes any residual surface carbon or metal catalysts that didn't integrate into the crystal. What remains is a pure synthetic miracle, ready to be shaped by the very tools it helped create. The engineering phase of construction is over, and the artistry of refinement begins. Because a diamond is the hardest material on Earth, you cannot simply cut it with a steel saw. To shape a lab-grown diamond, we use the power of light. High-powered, computer-controlled lasers are used to plot the best way to cut the rough stone to maximize its size and clarity. The laser doesn't cut in the traditional sense, it vaporizes the carbon atoms instantly, turning solid diamond into gas. This process, known as kerfing, allows technicians to remove the outer casing of the rough stone and slice it into the basic shapes called preforms. Every micrometer matters. If the laser is off by even a fraction of a hair's width, a potential 3-carat gem could be ruined. Modern laser systems are integrated with 5-axis robotic arms, ensuring that the angles are mathematically perfect for the next stage of the process, polishing. This is where the diamond's fire, its ability to split light into a rainbow of colors, is born. By using the precision of the laser, we can achieve geometric shapes that were nearly impossible to create with traditional manual methods, pushing the boundaries of what a gemstone can look like. The final step in the transformation is polishing. To polish a diamond, you must use another diamond. The stone is mounted in a specialized holder called a dop and pressed against a rapidly spinning cast iron wheel known as a scythe. The surface of this wheel is impregnated with diamond dust, millions of microscopic natural or synthetic diamond shards that act as an ultra-fine sandpaper. An artisan or an automated robotic system carefully grinds 57 or 58 tiny flat surfaces known as facets onto the stone. Each facet must be positioned at a very specific angle to ensure total internal reflection. If the angles are too shallow or too deep, the light will leak out of the bottom of the diamond, making it look dull. When done correctly, light enters through the top, bounces off the internal walls like a mirror, and returns to the eye in a brilliant display of scintillation. The precision required is staggering. Tolerances are often measured in microns. After a final cleaning, the lab-grown diamond is indistinguishable from a natural one, even to a trained jeweler using a magnifying loupe. It is a triumph of human engineering, proof that we can recreate the most beautiful products of the Earth, atom by atom. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.